Hello, welcome back. So we have the second talk of this morning from Professor Gautam Mandal from TFA Mumbai, who will be talking about bulk dual to SYK model from 3D.
And the mic is working. Okay, let me start by thanking the organizers for, the rest of the real organizers for inviting me to give this talk. And so I'm going to talk about a viewpoint of, a way of getting bulk dual to SYK models from 3D. So including the charged variety. And let me start. So since Juan has given a very nice review of the SYK model itself, so I will skip most of the introduction. So just to say that the SYK model is regarded as a simple quantum mechanical model of holography. Its low energy dynamics is that of pseudo Nambu Goldstone modes, which are described by this diff thing here means time reparameterization. So diff mod SL2R. So I would describe this thing, in terms of this action formulation that Juan wrote in terms of the sigma and G. More in detail when I go to the charged case, so just wait till then. But what appears from there is that there is a time reparameterization symmetry of the action, which is slightly broken and explicitly, but it's also spontaneously broken by the vacuum expectation value of some bilocal mesonic variable. So this has all been described by Juan, so I'm not going to. So basically it's spontaneously broken and it's also explicitly broken. And so these are our Nambu Goldstone modes. We call this pseudo Nambu Goldstone modes because of the explicit breaking. Okay, so the this symmetry. Okay, so the the low energy or the low action sector of the theory is described by this, and these are the ones which have found bulk duals. So let me describe several ways of arriving, trying to infer this bulk dual. So one is based on purely on symmetry reasoning. So just to remind ourselves, in the context of C equal to 1 matrix model, one used a pure symmetry-based reasoning to arrive at a bulk dual. So that worked in the way that the matrix model configuration space was a coadjoint orbit of W infinity symmetry, and geometric quantization of such orbits using coadjoint orbit quantization led naturally to the bulk dual, which was the two-dimensional string theory. So I can describe this after the talk if anybody wants, how that works out. Do we have such a symmetry-based reasoning here? Well, so it is known from the 1990 onwards that coadjoint orbit quantization of orbits of diff mod SL2R naturally leads to the two-dimensional induced gravity model of Polyakov. So, which is which consists of this R1 over box R thing. So that this was a demonstration for asymptotically flat spaces. So adapting from this work to asymptotically ADS2 geometries, one obtains a generalized Polyakov model which has a cosmological constant and appropriate boundary terms. And so this theory, okay, has a solution space which is basically given by large diffeomorphisms, okay, which are characterized by a time reparameterization at the boundary. And So the full nonlinear set of solutions of this model is given by large diffeomorphisms, which act on. So this is the metric in the conformal gauge. So it acts on the reference metric here, as well as it acts on this. So I'm not going to write down the full detail of this. So when I describe the second approach, I'm going to write down the nonlinear set of solutions, the full set of metric solutions in that context, in the Jacques-Teitelbaum context later on. But from this here itself, I would like to emphasize that the asymptotic diffeomorphisms, these are like the two-dimensional counterpart of the Brown-Hainour diffeomorphisms, and these are exactly known. Okay, these are exactly known. So you ask yourselves that what is the two-dimensional diffeomorphism which reduce to a time reparameterization at the boundary. So it becomes like f of tau. So tau tilde is f of tau at the boundary, and z tilde is z times f prime of tau, which has information about the scale factor. So this is the unique extension of this boundary reparameterization into the bulk in the Pfefferman-Graham gauge, and you can find out the metric by applying this exact large diffeomorphism and generate the full set of solutions. Okay, so I will come to the metrics which are generated by such things in the next method. Another natural way towards ADS2 bulk dual is to realize that ADS2 geometry naturally arises as near horizon geometry of extremal black holes. The S-wave reduction of higher dimensional gravity in this context leads to Jacques-Teitelbaum model. So this is how it looks. So basically, this is also something that Juan explained in detail. So if you don't have this, dilaton, the scalar field here, then this part is just a topological term, and it does not carry any information. But in this Jacques-Teitelbaum models, there's a scalar field which comes, which measures the departure from the the horizon region of extremal black holes or near extremal black holes, and the dilaton captures that information, so that's naturally there. But just as a two-dimensional theory, if you consider this dilaton as a scalar field, then it has some dynamics. However, the dynamics is entirely that of boundary degrees of freedom, because naively speaking, you might just do the simply speaking, you can do this degree of freedom counting. The metric has -1 degree of freedom in 2 dimensions, and dilaton has 1. So you have basically no propagating modes in the bulk, but it has boundary gravitons. And these boundary gravitons are given by large diffeomorphisms again of these things, and they're exactly given by these transformations that I said before. Okay, so the full nonlinear solutions are given by an orbit under the large diffeomorphisms, those large diffeomorphisms of the ADS2 Poincare metric and a 3-parameter dilaton. Okay, so this is the full solution is given by an orbit of the large diffeomorphism, starting from, let's say, this reference metric. So here I'm going to use Euclidean solutions for most part of my talk. So this is the Poincare metric, and this is a 3-parameter solution for phi. Note that so it's just these 3 parameters that completely specify this phi. Anyway, so applying this large gauge transformation that I mentioned earlier, this is the full set of nonlinear solutions of the Jacques-Teitelbaum model that you get here. So starting from here, just apply the usual diffeomorphism transformation to the metric and the scalar diffeomorphism appropriate to scalars, and this is what you get. Okay. And now for the specific example in which this f of tau is just the tan. Yeah.
In the previous slide, the solutions. So one mentioned there was an SL2R overall that you have to mod out by, which are kind of just moving things.
Yeah.
This ABC are part of that.
So these ABCs are real. Okay, these ABCs are so what actually happens is that there's a full set of 6-parameter solutions which you get, but these are the ones which stay.
So I see. So you've already modded out by the SL2R.
And you can see, by the way, this SL2R symmetry is easy to see from here as well, because the Schwarzian is invariant under that SL2R. So those Fs just don't appear in this thing. So, so by the way, I should remark here that this, the 2-dimensional metric has, so this is an exact form, and this is basically like in the it's a the Pfefferman-Graham gauge expansion for the metric just truncates, just like for this Bernoulli's metric in one higher dimension. And the large diffeomorphism here corresponds to normalizable deformation. So we will keep that in mind. Okay, so when you take the f of tau of this tangent form, then it converts the Euclidean real line tau into a circle of radius beta. Okay, the metric, so in that case, this metric becomes basically a black hole metric in ADS2, and with this as the the value of the horizon coordinate, and so the picture is that of a cigar in that case, because the d tau square coefficient of d tau square vanishes. And this relation, is obtained by, demanding that it's smooth over here. So that gives you the relation between Z0 and beta, where beta is the length of this tau circle. And so this is what happens to the dilaton in general when we apply the tan transformation. But here you can see that if you put this A minus C equal to 0, so A is equal to C, as well as B equal to 0, then you get this form of the dilaton. So we will keep in mind this form of the dilaton. So one was using this, the coordinates in which this was appearing as sinh square rho. So in that, this phi would appear as cos square rho. So we'll keep that in mind when we think of coming down from 3D. So basically, this information about the metric and the dilaton together would imply that it comes from a 3D BTZ black hole. Okay, so but we will come to that, of course, in detail. Yeah.
And overall 1 over Z outside, because upstairs we have.
Oh, excuse me. There is. Excuse me. That's a. Thank you for pointing this out. There is indeed, very importantly, 1 over Z here. Okay. Thank you. Okay. So this is the story of Jacques Teitelbaum, where we sort of motivated this as coming from extremal black holes in higher dimensions, notionally 4 dimensions onwards. However, there is a way of there is another way of using higher dimensions to obtain this bulk dual. So a natural way. So this was our motivation first, of course. Some of these remarks also appeared in one's talk. A natural way to look to liberate the single Virasoro group from the special QM context of SYK model is to think of 3D bulk. All I mean here is that quite naturally in 3D, okay, there's a well-known literature. I mean, there's a huge literature on ADS3 CFT2, which uses this large diffeomorphism transformations in 3D asymptotically ADS3 geometries, which are correspond to Virasoro cross Virasoro, as was shown by Brown and Heno. But it will turn out that although it is tempting to obtain, so this was our original thought, although it is tempting to obtain the one-dimensional Virasoro from a restriction of this, the Brown-Heno transformations are large diffeomorphisms which correspond to normalizable deformations. And so they do not naturally descend to Virasoro transformations in one lower dimension which contain non-normalizable deformations. So the dilaton, so precisely this 1 over Z factor which I was missing, so that makes it a non-normalizable deformation, which is necessary to capture the SYK physics because you are turning on 1 over J. Okay, so you're going away from the IR fixed point, so you are turning on a non-normalizable, you are turning on an irrelevant operator, so that corresponds to non-normalizable deformation. So therefore, the Brown-Heno transformations by themselves are not tailor-made to, at least just not by restriction of Brown-Heno. It's not, so in this talk, that's what we will consider some other realization of, the Virasoro symmetry in 3D, which is not Brown-Heno, which will contain non-normalizable deformation, and they will descend to the Virasoro of in 2 dimensions. That is this how much is left? 37 minutes? Okay. Okay. So no, I'm doing fine. Good. So this is the excuse me. Okay, so this is the plan of the rest of the talk. Kaluza-Klein reduction of, so this is what, so I'll discuss first Kaluza-Klein reduction of Einstein gravity from 3D, which will give JT theory. This actually has a history, this is known from 1993 onwards by work of Achukaro et al. And also later developed by Castro et al. I will give you those references as I go along. And who also showed that a BTZ black hole, the Kaluza-Klein reduction of the black hole gives you ADS2 black hole. So what we did, of course, is to use this technology to apply to the SYK context. And so first of all, as I said, I will show you the non-normalizable Virasoro transformations in 3D, which descend to large diffeomorphisms in 2D of the kind that I have already mentioned. After this, I will go to the charged model. So first, I will describe the charged SYK model very briefly in one slide, I think. And then also, mention the effective action of the Goldstones, it will have a new set of Goldstones now corresponding to U1 symmetry transformations. So the charge model will have the following bulk dual coming from 3D, which is Einstein gravity plus E1 Chern-Simons term in 3D, which will give rise to Jacques-Teitel-Boehm plus a BF theory in 2D. And so I will describe then how the Goldstones of the field theory model are realized in terms of the Virasoro and large U1 gauge transformations. So both in the 3D and 2D versions, and the effective action of these Goldstones will reproduce correctly the charged SYK model, which has a Schwarzian plus a sigma model term. That's the new term. And I will very briefly, if time permits, very briefly mention the calculation of quantum chaos in these models and then summarize. Okay, so let's go. So we will first look at the Kaluza-Klein reduction of the black hole, and then we will go to the dynamics and the Lagrangian later on. So this is some, as I said, Achukaro Ortiz, this should be 93. Sorry, this should be 93. And Castro et al., 2008. So here I have used the L equal to 1 convention. And this is what the BTZ black hole, the non-rotating BTZ black hole is in these coordinates. And I will take the the periodicity of tau to be beta, and this coordinate y to be 2 pi alpha. So this is beta and this is 2 pi alpha. And so the validity of the Kaluza-Klein reduction is the following, that the asymptotic radii of space and Euclidean time circles are, as I said, 2 pi alpha and beta respectively. And for the Kaluza-Klein ansatz to be valid, okay, this radius should be much less than this radius or any other length scales in the final theory that you were interested in. So, which translates to the following, that the temperature or the energy scales of interest of the theory should be much, much less than the Kaluza-Klein mass scale, which is the inverse Kaluza-Klein radius. And that is of the order 1 over alpha, excuse me. So, and we will shortly identify this alpha to be 1 over j, okay, where j is the coupling constant of the SYK theory. So, in when we sort of match with the field theory, and therefore the Kaluza-Klein, the condition of validity of the Kaluza-Klein ansatz coincides with the IR condition. Okay, so that is something that we felt very happy about. So this Kaluza-Klein condition became the same as the IR condition, and so which ensures. So this IR condition is the one that ensures that we are near the IR fixed point. So this is that condition which appeared also in one's talk. Okay, so that's the, so now that, we have ensured that there exists a regime in which we can do the Kaluza-Klein ansatz. So let us see whether, so first of all, the black hole solution itself, we can, so this is our Kaluza-Klein ansatz. We take a three-dimensional metric and write it in this form. So the, so I have used notation here in which y is, so instead of the y variable, so when I write the Kaluza-Klein ansatz, I will not write dy here, I'll write d theta. So just to have a normalization convention of what phi is. And so y is related to theta by y is equal to alpha times theta, where the proper radius of y was 2 pi alpha. So that's what it is. And so clearly, if you remember what the metric is, so it's clearly, this part, okay, we can identify with the two-dimensional black hole metric, and this will be my phi square. And since there is no cross term here, so the Kaluza-Klein, what would have been the Kaluza-Klein gauge field is actually 0. So the dilaton turns out to be, in this context, exactly the same way as we had found from the solution of the JT theory. Okay? So, and that, in fact, is not surprising because indeed, under the Kaluza-Klein ansatz, this one, Einstein gravity in 3D just boils down to, Einstein gravity in 3D, which is this, okay, it boils down to the JT theory. Okay? It boils down to a generalized JT theory in which there is a field strength term of the Kaluza-Klein gauge field. But for simplicity, and it is also possible to do so consistently from the equation of motion, we will set the Kaluza-Klein gauge field to 0. Okay, so so note that so this is the Jacques-Teitelbaum term with the boundary term here, and and indeed the most general solution of the JT theory, Jacques-Teitelbaum theory, constitute the most general solutions of 3D Einstein gravity consistent with the Kaluza-Klein ansatz. So. So what I mean to say is that we found in the Jacques-Teitelbaum formulation the most general set of solutions, and because of the equivalence of the Lagrangians here, okay, one can show that these are the most general solutions of the 3D Einstein gravity, which is consistent with the Kaluza-Klein ansatz. And they are given by this form. So what was written earlier as the dilaton, its square now appears as GYY. Okay, so that so this is the full form of the 3D metric. Okay, so if you notice, this part has only normalizable deformations, but this part has non-normalizable deformations, and in the sense that the 1 over z square part of GYY, that is something non-trivial. So these have non-normalizable deformations and hence are not a subset of Brown-Henner deformations. Okay, so similar solutions of 3D Einstein gravity with asymptotic symmetries which have non-normalizable deformations and different from Brown-Henner transformations have appeared earlier as well. So this is an example which appeared in the first in the paper of Compare, Song and Strominger, which was generalized later by Nemani and collaborators here. So this is some theory in which the asymptotic transformations are U1 cross Virasoro. So the Virasoro part is normalizable, and it's a subset of Brown-Henner transformations. But the U1, okay, as you can see, it has both non-normalizable part and a normalizable part which depends on the non-normalizable part, pretty much like here. So there is a non-normalizable part here, and the various normalizable deformations depend on that. So there's a one one Virasoro set of transformations in this way, expressed in this way in the 3D metric. Okay. Yeah. Hi.
Are these solutions finite action? Like, do they have finite action or?
These solutions do have finite actions, as I will show. So the action cost of these F transformations does turn out to be precisely the Schwarzian.
They don't enter into the action. I mean, when you compute the action.
They do. Yeah. I will come to that. Okay. Yeah.
And they have a counterpart in the SYK.
Yes, indeed. So the boundary value of the dilaton, okay. So that is basically that corresponds to the 1/j parameter. So the boundary value of the dilaton, which in principle can involve A, B, C parameters, okay. So that does enter the Schwarzian calculation.
Solution of the SYK model. How would you relate the ABC to?
So it just went. The ABC combination, whatever went into the value of the dilaton at the boundary. Okay.
There is this parameters alpha n.
N alpha s by j. That was what came from SYK.
Yes.
And this parameter gets related to the boundary value of the dilaton from the SYK.
But that's some combination of ABC.
Yes.
But the other degrees of freedom. There are 3 parameters here, and there's 1 parameter there. Do they correspond to something, or some special combination that you're saying which corresponds to that parameter?
There could be a significance of, maybe Juan can say something on this one. So there could be some significance of the 2 other parameters, but
The thing is, in any particular coordinate system, you impose a boundary condition which is dilaton at the boundary should look like a function of phi, a function of time, boundary time divided by the cutoff. So you choose in any coordinate, in any f, you choose this ABC such that it looks like that. So dilaton is can have a function sitting, a time-dependent function sitting at the boundary. So it's okay to have 3 parameters, and then you choose a boundary reparameterization to just set this function of time to a constant. So even in the SYK model, you're allowed to have a function sitting, a time-dependent function as a boundary condition for the dilaton, which can have 3 parameters.
But Rajesh's question is more like parameter counting, so.
Maximum deformation, right?
Yes.
For GYY.
Yes.
And the extra parameters pertain to, therefore, the sources for the boundary stress tensor that you are turning on, right?
Yeah. So in a way, the simplest choice would be to take A. Okay, and that would have the direct interpretation in terms of 1/j, and the other guys might have something, but
more generally, you have some time-dependent source that couples to TYY. Is that one way to think about what you're doing in the boundary?
So actually, the Schwarzian action is it will have a, so let me just go to that one. Here it is. Okay. So the way the Schwarzian appears is by having a dilaton here, okay, and this Schwarzian term. So let me just say what I was going to say here. So the effective action of these things can be computed from the 2D version, which is already done. So what happens here is that you have the dilaton appearing here, okay, and that's not a constant in general, okay. However, you can treat this Schwarzian action as describing, the action, off-shell action of the F degrees of freedom. Okay. Remember that the F's are now part of your path integral because these are large gauge transformations. So you have some path integral here with phi, the boundary value of phi, okay, as a given Dirichlet boundary condition. So your path integral is actually functional of that phi. So the correct way to think of it is that phi sits here, which is an externally specified value, which you can take it to be constant. And then the idea is to determine F in terms of that phi if you want to look at the saddle point. So the expressions that I have been writing for phi in terms of F is to be more thought of as an expression of F in terms of phi. Okay, so this is what Advait was trying to say. And so that's...
Yeah, thank you for that.
Yeah,
but
yeah.
Your formalism would allow phi to also depend on tau, right? That is,
indeed,
you can choose it to be constant, but
indeed. So I can put a, so if it is like an externally specified value of the boundary condition of the dilaton, it can very well be a function of tau as well. Yeah. But if it is so, then however, so this is what Juan has shown and his collaborators have shown in this paper, is that if there is a time-dependent phi sitting here, then you can make a change of the boundary clock, okay, so that can be made into a constant. Okay. So eventually, there is only one parameter that stays in that thing, and that one parameter has to be identified with this 1 over j. So that's the thing.
Gautam? Here.
Yeah, hi.
Yeah. So the boundary metric in ADS3, does it depend on ABC?
Boundary metric on ADS3 does depend on ABC, yes.
So after you remove the Z square and so on and so forth. So,
Yeah.
So the CFT2 is seeing some metric which has ABC in it.
That's right. That's right. The ADS3 metric sees ABC in.
So the ADS3 metric has it, but I'm asking about the boundary metric. The CFT2 metric, does it have ABC in it?
That is correct. Okay. That is correct. So it would be a CFT2 coupled to some boundary metric which will have an ABC. Yeah. And of course the F.
CFT2, you are Kaluza-Klein reducing with putting some complicated metric on the
CFT2.
You have a warped metric. The circle, the way the circle is fibered over the time,
right,
is something complicated, and that is specified by ABC.
That is right.
That's what you're doing into CFT to try to get something which looks like SYK.
That is correct. That's correct. So okay, this interpretation of phi bar. So okay, so there's exactly going by that remark. So this phi bar basically gets identified with the proper circumference of the time circle. Of the y circle, and which I had, the third dimension, which I had called alpha. So therefore, by comparing this with what we have from the SYK model, this alpha gets identified with 1 over j. So this is some identification which I had already used in the discussion of the Kaluza-Klein thing. So here, alpha was taken to be 1 over j. So this is the proof now. So here, it's not like we are just we are just proposing that there is a 3D Kaluza-Klein point of view for the bulk dual as well. And this calculation, as soon as you realize that it's a JT theory, of course, the Schwarzian calculation you don't have to redo. Okay, so you just declare that. Okay, so this could all be inferred from the works of Achukaro et al. And Castro et al. So on. But you have to sort of adapt this to the SYK context. Okay, so just a remark about what happens to the rotating BTZ solution. So here, indeed you have coupling terms like d theta d tau, which corresponds to Kaluza-Klein gauge field like that, and this is the 2D metric. So in this talk, as I said earlier, we'll set the Kaluza-Klein gauge fields B mu equal to 0 for simplicity, and hence will not consider the rotating solutions further. However, of course, there is an interesting issue of if you take the extremal rotating BTZ and whether there is something similar to the higher dimensional physics that happens here. And that would be another way, perhaps, of getting ADS2 physics from 3D as well. So this is something that I'm discussing with Sandip and the collaborators. And yeah, hi.
Put the B mu equals to 0, will you put J equals to 0 for the beta is non-zero? Right?
That's correct. That's correct. So that is why we are taking the non-rotating situation, just to have the Kaluza-Klein gauge fields equal to 0. That this is only, this was not done for any conceptual obstacle, but for simplicity, because as soon as the Kaluza-Klein gauge fields came in, they made the analysis of the theory quite difficult.
So this Kaluza-Klein could have been done even without a rotating black hole. Means
Kaluza-Klein
started with a rotating
done,
and then
without rotating black holes, of course, because the general so the general thing was this. Okay, if you start from Einstein gravity, you do have. Okay, so I should say what the notation is. This F tilde is the field strength corresponding to this Kaluza-Klein gauge field. Okay, so the general thing is this. This is JT, Jackie-Teitelbaum model, which was this part, and the corresponding boundary thing. And this is the additional part, which comes from the Kaluza-Klein gauge field, which makes life a little more difficult. Okay, so the summary so far. So the Kaluza-Klein reduction of Einstein theory in 3D reduces to Jackie-Teitelbaum model. The the dilaton comes from the radius. As I said, the symmetry breaking by a small dilaton in the Jackie-Teitelbaum model gets a geometrical interpretation in terms of a small non-zero Kaluza-Klein radius. Okay, and the Kaluza-Klein, so it's a little differently realized than for extremal near horizon region of extremal black holes. So here it's if you switch off, if you go to the zero limit of the Kaluza-Klein radius, then of course you recover the ADS2 black hole itself. But if you turn on a little bit of non-zero Kaluza-Klein radius, that's equivalent to turning on a small dilaton. So the picture is quite different. So so this is something that I have just mentioned, that the asymptotic, the two-dimensional Virasoro transformations can be sort of captured by some, by large diffeomorphisms in the ADS3, and the metric solutions, show non-normalizable deformations corresponding to the non-normalizable dilaton. Okay, so that's, and the regime of validity of the Kaluza-Klein reduction coincides with the IR regime, and the Schwarzian effective action of the time reparametrization thing comes out. Now let's go to the charge model. Okay, the charged SYK model is described by, so replacing the Majorana fermions by complex fermions and Q-body interaction Hamiltonian. So for Q equal to 4, it would be just like, psi I dagger, psi j dagger, and psi k, psi l. And then there are reality conditions, which makes this overall thing real. And so the random couplings, they are subject to this reality conditions, and they are given by Gaussian distribution with this expectation value of the square of the j is like that. Okay, so it's pretty similar to this thing. One can easily see that this model has a global U1 symmetry. Okay, the number of psi daggers and the number of psis are the same in the Hamiltonian, and the corresponding conserved charge Q. The theory can be described by the conjugate chemical potential mu. So, as in case of the uncharged model, okay, so this kind of a action appeared in Huan's talk in the morning, as you saw. So this sigma is tau 1 tau 2 is the bilocal self energy, and g tau 1 tau 2 is it was like the now it will be like psi dagger tau 1 psi tau 2. So that's the bilocal meson with like one charge 1 object at tau 1 and charge -1 object at tau 2. And the structure of this action is slightly different from before. Now tau 1 tau 2 and tau 2 tau 1 inside G makes a difference because you have to have the so you have to have the charges working out. So now so you can see more or less from this action itself that, okay, so first of all, it's clear, if you just look at this term, let us try to infer the symmetries of the problem by looking at this term of this thing of the Lagrangian. Clearly, if G T1, T2, okay, is like a tensor of the weight 1 over Q in terms of reparameterization. So then this is Q by 2, this Q by 2. So overall it's Q. And if it's a tensor of weight 1 over Q, then that exactly matches and compensates for this d tau 1 tau 2 measure. So basically what I mean to say is that this part was already quite clearly a symmetry of the problem. And now you can see that there is this additional, additional. So in the IR limit, okay. So when I'm looking at this term, you can also assign a similar transformation to sigma, okay, which is just the sort of complementary transformation property to this, and this term basically is gone. And so let me not go into the details of this, but let me just tell you that the symmetries that you sort of figure out by looking at this term are really the symmetries of this action in the IR limit. Okay, and so the additional symmetry here is basically the thing that was the global symmetry now becomes a local symmetry. Okay, so each bilocal meson picks up transformation corresponding to charge 1 at tau 2 and charge -1 at tau 1. And at the IR limit, just like before, where the scaling symmetry became a local symmetry, now the global E1 symmetry becomes a local E1 transformation symmetry. So now we have two sets of Goldstone modes, which called so f of tau, this tau tilde as a function of tau, that is the old reparameterization zero modes, and phi of tau are the new U1 zero modes. Now the picture is pretty much like before. The wave of G, okay, which is given by the fermion 2-point function, it looks like this now, and it breaks this local version of Virasoro cross U1. So I have put a quote around the cross because it's not really a product group. It makes the difference whether you do the Virasoro transformation first and then U1 or the other way around. So this group is broken to SL2R cross global U1, and you have a coset structure of this. And so as in the so the uncharged case again, this Goldstone modes exactly at IR, they don't have any action at all. As a result, again the theory would be singular. So you have to turn on some 1/J, and so the action that you pick up, okay, has the old familiar. So this is from the field theory analysis. I forgot to mention that this is, I think I did. So this is in a paper of Suvrat et al. From 2016. And so it has the familiar Schwarzian term, but then it has a sigma model term. And the coefficients here are both proportional to 1/J. Okay. But there's a new constant that comes in, which is the ratio of these two things. Okay, so now let's go to see how we can get a bulk dual of this. Clearly, we have two sets of Goldstones. The new ones are the the E1 Goldstones. So we now need large U1 gauge transformations. Okay, so some gauge field in the bulk. So what bulk model has this? So we again start from 3D. We find that to be rather convenient to do so. So the appropriate model turns out to be Einstein gravity plus E1 Chern-Simons plus a coupling term. Okay, so the Chern-Simons action is given by this. So this is a boundary term which is possible to add in asymptotically ADS3 geometries. So this K is a real positive number here, and
where K is an integer which is required by gauge invariance.
But but this is this is SL2. So this is U1.
Ah, I see.
Right. So now, although the boundary term introduces a coupling of the okay, so this one actually introduces a coupling of the boundary U1 to gravity. So the field strength equal to 0 condition is still valid even with this boundary condition. So that gives rise to the following issue, which is that so in a for example in a black hole geometry where I have a contractible time circle. Okay, so here at this end, clearly the Wilson loop has to vanish. Okay, and the field strength is 0 all the way in the middle. So therefore, the Wilson loop has to vanish here as well. Okay, so eventually, however, we would like to have a Wilson loop along this non-contractible time circle at the boundary, because that is the one that is going to be identified with the chemical potential. And as a result, this situation, therefore, we have to correct for it. So how do we correct for it? So we basically add a coupling term between the Chern-Simons fields and gravity in the bulk coupling term, which is in terms of some external source here. And I will soon, so now we do the Kaluza-Klein ansatz for the gauge. Okay, so there's a bit of detail. So the Kaluza-Klein ansatz for the gauge field now will have a spin 0 component here. And And similarly, the external current, okay, that can only be under, the consistent with the Kaluza-Klein symmetry. It can only be of the following form. So first of all, JT and JZ, they both have to be 0. Any one of them non-zero will spoil that symmetry. And JY, okay, has to be constant. Okay, you can, so that just becomes so basically the entire content of this coupling, the external current, becomes just a constant. Okay. Now you do the KK reduction, and these are the terms that, can I just get like 5 minutes, 2 minutes? Okay, all right. So this is the scalar times the F term. So this is the BF term, and this is the coupling thing. And you, and these are the boundary terms which you can more or less read off. The interesting boundary term is the one which is phi a tau squared, which comes from the coupling term of the original E1 Chern-Simons theory itself. And so you can now, so the full set of Euler-Lagrange equations of this, okay, so these are the Euler-Lagrange equations. You can show again that the Kaluza-Klein gauge field as well as the spin zero, component of the Kaluza-Klein scalar, they can be put equal to 0, and the remaining equations become this. These two equations are the same as the gravity equations as before, and the field strength now has this, J naught constant in it. And so the solution set is, schematically pictured like this, that you start from ADS2 and constant, value of A naught. So then in AZ equal to 0 gauge, it just becomes like a constant value of A naught. And then you make simultaneous large diffeomorphism and large gauge transformation thing on it, and you generate all your solutions. So I'm not going to write down this thing, I'm just showing this picture. And then, so the transformation acting on the gauge field is just this. And basically, okay, so now, this is just to say that, here you see that the field strength is proportional to that coupling. And if you apply Stokes theorem in this part, Wilson loop vanishes here. So the Wilson loop here picks up the, J naught. So basically, A tau gets proportional to J naught. So mu, so the boundary value of A tau is to be identified with I mu. This is the standard identification between chemical potential and the gauge potential A naught. And so if you do all that, so essentially what happens is that the A tau picks up a gravity transformation. That's this tensor part. I mean the Jacobian part, and it has the large gauge transformation. So it's this A tau square. It just becomes this thing, and that's precisely the sigma model effective action that you got from the charged SYK model from Sachdev et al.'s calculation with some obvious identification of parameters. Okay, so just one mention of the quantum chaos calculation. Basically here you had a non-trivial Lyapunov exponent because the propagator, was like, the propagator there was 1 over omega fourth minus 1 over beta square omega square. Okay, so you got, therefore, there were solutions which were like 0 and plus minus beta. Okay, this was what came from the Schwarzian. And now, what will come from the new sigma model term is just 1 over omega square. So it does not have any non-trivial poles, therefore it has 0 Lyapunov exponent. And So I can explain this calculation to people later on after the talk. But so here's the summary. This is a summary of the charge part. I have already summarized the other one. So the bulk action for the holographic dual of low energy sector of charge SYK is obtained from a 3D formulation. It consists of 3D Einstein gravity with negative cosmological constant, U1 Chern-Simons, plus a coupling term, plus boundary terms. I have explained all of these. Under KK reduction, this leads to a GT model plus a BF term plus coupling plus boundary terms. We derive a consistent truncation in which the KK gauge field from the 3D metric and the KK scalar from the 3D gauge field can be set to 0. The coupling term is the additional parameter in the charge model which corresponds to the chemical potential. The effective action of the large diffeomorphisms and large gauge transformations is found to be a Schwarzian action plus a sigma model term as predicted from the SYK analysis. We compute the OTO correlators of charge operators and find that the boundary photons contribute to zero Lyapunov exponent. Thank you. Yes.
So in the first part of the talk, you mentioned that this Kaluza-Klein limit, you showed that it corresponds to the low energy limit of the SYK.
Right.
Now that you have introduced a chemical potential in the SYK, it introduces a scale, right? So that limit works out, means straightforwardly.
Works out again. Yes.
Straightforwardly.
Yes. Hi. Yeah.
The extra boundary photon doesn't contribute to the the Lyapunov exponent.
That's right. Basically, yeah. So the way it appears. So let me just go to this thing. Yeah. So it has some Schwarzian of f. That's the first term without. Now the new term is this. Now here, in fact, you can just do a field redefinition. Okay, shift your definition of phi. Okay, so that it just decouples from the other part. And so what I'm saying is that you define your phi tilde as so what you have to do is define phi tilde is equal to this. This actually is a constant. So phi tilde is equal to phi plus a tau f. So when you do that, okay, in terms of the new phi tilde, okay, first of all, it's decoupled. That's fine. It's decoupled is fine. But its propagator is trivial. That's the main point, that the propagator is trivial. Okay, like in the other one, if you look at the theory of f prime, so the f, if you write f equal to identity plus epsilon, then it was quite non-trivial. So this is how it was square. Okay, so that is what gave you this thing. And basically the appearance of the poles at plus minus beta, of course these were supposed to be the gauge modes. So we are supposed to not take them into account, but some rather beautiful things happen. So it is I omega tau, and you do this in integral. Actually, these are the sum over the n all Matsubara frequencies. You have to do this sum. And in that, you were supposed to okay, so this just becomes, this beta just goes away when you make, okay, so omega is scaled appropriately so that in terms of n, it just n to the power 4 minus n squared. Okay, so n equal to 0 and plus minus 1, you have to delete from the sum. So, okay, it's not that. All the rest of the integers are there. And this sum then can be converted into an integral, okay, in which you can do some contour deformations so that, it's so these three guys, you're supposed to you are supposed to omit. So everybody else is there. Okay. Now you convert this into an integral by using the usual thing of series sum, make it into some sinh tan hyperbolic or whatever it is, and that integral, okay, has to begin with its life. It has contributions from these things, but after some appropriate contour deformation, you can deform it like this, and it gets contribution only from here, back again. Okay, so it was important that you had some non-trivial pole structure here. Okay, and that's what does not work out with the other, the omega 1 over omega squared propagator.
If there are no further questions, let's thank Gautam again.